Have you ever wondered how to replicate the complex dome design of the Louvre Museum in Abu Dhabi designed by Jean Nouvel? In this video tutorial we'll show you how to use both Rhino and Grasshopper to achieve a similar result. Our process will begin in Rhino, where we'll generate a single model. From there we'll move on to Grasshopper, where we'll transform the shape into mesh, place it onto 4 different square grids that are projected on the dome surface. Once we have 4 different layers, we'll apply thickness to each model and get the final shape. So let's get started. Let's take a closer look at the project images, both from outside and inside, to gain a better understanding of the project complexity. From these images we can see the dome structure is composed of various layers that can be divided into 3 different groups. Outer one, which has 4 layers, then we have truss structure, and inner one with 4 layers as well, similar to the outer one. In this tutorial we are going to focus only on one group of 4 layers, either inner or outer one, as they're very similar. We'll begin with creating this model in Rhino. The first step, we'll create 2 different elements, offset each one with 2 different offset distance. We're going to load them and create the polysurface for each element. In the next step, I'm going to draw the polyline offset 2 times with the same offset distance as previous elements, create surface with a loft. Then we're going to distribute this polysurface at each corner, creating the final shape. And in the last step, we can join them and create a single polysurface. So in the first step, I will take rectangle command. Let's type dimensions of the square, let's say 5 by 5. Then I'm going to select it and I will type scale, copy yes, turn on center snap. This will be the center of scaling, and now we'll need to type scaling factor 0.356. This is approximately, but around 0.3 should be. Enter. The next element should be triangle, uncheck center, closed polyline. Once I have these 2 polylines, I'm going to offset them. So the first offset distance will be 0.05, and I'm going to offset them inside. Another offset distance will be 0.2. The offset curve will be offset by 0.2. In the next step, I will use loft command to create the polysurface. I will select first pair of polylines. We'll create the first one. After that, I will create another polysurface, selecting another pair of polylines, and the same logic here. First pair, enter, and another pair. After that, I'm going to join these 2 and these 2 as well. After that, I will select triangular polysurface, orient them, check here, copy, first reference point, second reference point, first target point, second target point. We can use mirror to place it here and mirror as well to place it above. In the next step, let's create a polyline here, and I will offset them with the same offset distances that we offset the previous elements. First 0.05 and 0.2. Then I'm going to trim these 2 polylines. After that, I will select first pair of polylines and create polysurface. Also select another pair of polylines and create another surface. Alright, these 2 polysurfaces I'm going to join. Once we create a single polysurface, I'm going to place it in upper right corner. So with the orient component, don't forget to check here yes. We need first reference point, second reference point, and we need 2 target points. And I will take this guy here, mirror, and to position at the down left corner. I'm going to select all polysurfaces and I'm going to join them. And once we create a single polysurface, I'm going to reference it in Grasshopper. As you can see, we already have a simplified site model. This is just for the sake of context. So I'm going to take point container and I'm going to reference the point. Our idea is to create a dome surface first, and on that dome surface we are going to project a square grid. We will take the model and place it inside the grid. We know that the height of the dome is around 27 meters, so I will use component move along Z direction by 27, and we know that the radius of the dome is 100 meters. I will create a circle. This is center of the circle, and this is radius. We have the radius and we have the height. I'm going to find 2 points on the circle, and using these 2 points and the point that we moved along the Z direction, we'll create a sphere. Let's evaluate this circle. Reparametrize, and in the input I will type 0 and 0.5. which is the start point and middle point of the circle. Right, once we get these 3 points, I'm going to merge them and I will place them inside single list. So I will flatten this list and place in the pin. But we only need one part of the sphere on which we are going to project square grid. Let's create first square as an outline of that grid. This will be the center of the square, and we need to define dimensions. And domain should be from -100 to 100. But instead of using 100 to 100, I want to extend this square just a little bit. Should be something like this. Just the square should be a little bit larger than the radius of the circle. So for that, I'm going to multiply this 100 with a multiplication factor around 1.1. And let's create the outline of the grid that we're going to use. It should be from -110 to 110. Now you may wonder, okay, I'm going to take this rectangle, project on the sphere, and we can trim the sphere with project the curve. But once we get this surface and try to divide this, we'll get an error because this will be trimmed surface. Somehow we need to take this outline and create untrimmed surface from it. Instead of projecting on the square on the sphere and getting trimmed surface, we'll do another method. I'm going to explode rectangle and I will extract 2 opposite segments. So let's extract segments 0 and 3, these 2 lines. I'm going to divide these 2 lines by the same value, 50. So I'm going to divide this by 50 in order to get 51 division points. Don't forget to reverse the list. Now these lines we're going to project on the sphere with the component project. Here we get sphere curves to project and we get 2 set of curves and we need just upper part. So we can extract middle point of each one and we can sort them by their Z value. So we can use deconstruct point. All right, sort them by their Z value. And by default is set to 0. But if we reverse the list, now we get only these curves. We can simply use a loft to create a surface. We don't get the surface because inside each branch we have a single curve. But if we trim 3, inside 3 we'll get 51 curves and now we can create a surface. As a result, we get untrimmed surface. This is really important because now this untrimmed surface we can divide, create the grid, and we can position our model inside each grid. I want to create these 4 layers and they're slightly rotated from each other. Let's say this is position. Now I'm going to rotate this guy by 5 degrees, by 15, and this one by 25 degrees. So I will type use rotate plane and plane will be XY plane. So this is the plane where the rectangle is positioned. So instead of having a single plane, as we have here, we'll create 4 different planes. And I will check here degrees. Now we need to create 4 different angles. From let's say 0 to 60 will be slider. So original position is 0, then let's say 5, 15, and 25. Or maybe this can be 25 and this 35 to be more versatile. And I'm going to merge and place it in the angle. So now we have 4 different planes. If I place 4 different planes in the rectangle, we'll get 4 rectangles. And now let me check what we get here. We have 4 branches, inside each branch 51 line. Once we project them here, we have the result that we need. And we get 4 untrimmed surfaces. But these surfaces shouldn't be in the same position. They should be offset vertically in order to create 4 different layers. And let me explain here. So we'll get 4 different layers of models, and each model will have a different thickness. So based on their thickness, we need to position all 4 layers. So first, let's define the thickness of each model. The first will be 0.3, 0.18, 0.14, and 0.2. All these dimensions are like approximate. This is how I define the thickness, but you can set another numbers if you want. Now let's go back in the top view. The offset distance will be 0.3, and this is how we can get surface 2. Now we need to get surface 3 and 4. Surface 3 will be once we sum these 2 numbers, which is 0.48, and surface 4 will be at position of 0.3 plus 0.18 plus 0.14, so we'll get value 0.62. This is third offset factor, and this is how we get position of the surface 4 or the layer 4. As our surface is smooth, and that smooth surface will apply rectangular or actually square grid, we'll get jagged surface, and we might get some intersections of the models between the layers. That's why we need to create the gaps between the layers. I define gaps in my case 0.1, but you can set another value if you want, and we get something like this. In the top view, I will explain you how we'll get different offset values of the surface. The surface 2 will not be positioned at 0.3 anymore as we have here. It will be positioned 0.3 plus the gap. In my case, gap is 0.1, and the offset will be 0.4 in order to get surface 2. Surface 3 will be once we sum the first offset plus the gap plus the thickness of the layer 2. And this is 0.68, and then we have the surface 4, which is 0.68 plus 0.1, which is the dimension of the gap, plus the thickness of the layer 3, and this is 0.92. This is how we created offset distances of the surface. All right, let's go back here. So we need to offset this sphere surface. I will type offset surface. And now we need to define these offset distances. Let's define first thicknesses of each model, these 4 numbers. Once we create thicknesses for each layer, I'm going to place them in the separate branch with the entwine component. So you need to go here +1, and we get 4 branches. Inside each branch we have the thickness of each layer. In order to get offset distance for the surface, we need to add the gap that I mentioned. In my case, gap is 0.1. So I will add each of these number, the gap value, and we get 0.4, 0.28, 0.25, and 0.3. Now we need to create offset distance, and we can get this value with this component. I need to flatten this. This is 0.14, my mistake. And we get the same value that we get here, 0.4, 0.68, 0.92. But we don't need 1.22, and we need a number 0 at the beginning because I want to preserve the position of the first surface. That's why I will use cal index. So we don't need the last number in the list, and I will add to this list 0 at the beginning. Flatten the list, and we get offset distances for the surface. Don't forget to graph, because we need to get 4 different branches. Each surface should be placed in a different branch, and now we can place it here. And these untrimmed surfaces are not overlapped anymore. Now we can divide each surface with the ISO trim and divide domain component. We also need to set the number of divisions along U and along V direction. And if we turn on this picture once again, you can see that the difference between the layers are the angle and also the density of the pattern. First one is the less dense, and the third one is the most dense, which means the number of UV divisions should be different for each layer. I'm going to use entwine component once again, 4 branches. In the first branch, 24. This is the smallest number, and we know the largest number should be in the branch 2, and in the branch 3 should be larger than this one, but smaller than these two. And I will play the same number in the U and the V. Once we divide each offset surface, we can now position our model. Let's first reference the model inside Grasshopper with the BREP container. So set one BREP. Because the calculation will be faster, I'm going to convert this BREP into mesh. So we can use simple mesh, and instead of having polysurface, we'll get a mesh. Also, we'll need the outline of this model, and we can get the outline with the bounding box. Now we can use deconstruct the BREP, take the surface, and get the polyline. Here we get the mesh, and we get the outline. All right. So what is the easiest way to position the model inside these divided subsurfaces? So we can use box morph. The base geometry will be the mesh. Then we need reference box. We can easily create with the component box rectangle. So the base rectangle will be the outline of the model. And for the height, we need to place domain, let's say from 0 to 1. Okay, and this is a reference box. Now we need to create a target box. Target box we can get from the subsurfaces. We will use component surface box. Base surface, this one. Domain is the same as domain that we have here. And the height is really important. Height of the surface box should be these values: 0.4, 0.28, 0.24, and 0.3, which we can see here. So this will be height of the boxes. So this is the first height, second height, third, and fourth. I'm going to flatten this one here, because here we should get unflatten. Unflatten, actually, all these values should be placed in a separate branch. And these values I will use as a box height. Let's zoom in here. We get target boxes, and I will place in the T input. You can see how easily it's calculated, because as a base geometry we have mesh. Let's extract a single branch just to visualize the result. We get the first layer, but now we need to apply thickness to this mesh. To explain you better how we're going to apply thickness to our mesh, I will open this diagram, and we are going to use component naked vertices. With this component, we'll separate naked from the clothed or inside vertices. Blue ones are naked, red ones are clothed vertices. Once we get that, I will take blue points or blue vertices, and I'm going to move them along normal direction. Let's go in the perspective view by the half of the height of our layer, which in our case for the first branch will be 0.15, then 0.09, 0.07, and 0.1. So this will be the normal amplitude of translation vector for the naked vertices, and we'll get one part of the mesh, which looks like this. Upper part of the mesh we'll get if we take inside or clothed vertices, or these red points, and if we move them along normal direction by the thickness of our layer, which is 0.3, 0.18, 0.14, and 0.2. Naked vertices stay in the same position that we previously created, which are placed on the half of the height of the layer, and we get upper part of the mesh. Once we get these two parts, I'm going to join them and create closed mesh. So first I will take component from the ViewBurst plugin, join mesh and weld, and in the W input I will set a boolean value true with the toggle button, and I'm going to connect the mesh. Basically I want to join any of these four meshes. It will take a couple of seconds to calculate it. Alright, now I'm going to use previously mentioned component naked vertices. We can separate naked vertices from the clothed ones. Here we have the inside vertices, here we have naked. And here we have, which is really important in our case, their index value in the list. First, I will take naked points, and I'm going to move them along normal direction. Normal direction we can get if we deconstruct mesh. Here we get normals, but I need to take normals only for naked points. We can do this if we use index values. So we have index values of the naked points, and I will apply to normal vectors. So here we have normal vectors, here we have points. And now we need to set amplitude. Amplitude should be half of the thickness of the layer. I will take numbers from here and I'm going to divide. Once we get vectors, I'm going to move these naked vertices so we can now construct the mesh. Before we construct the mesh, we need to place these naked points back in our list at their original position. Here we have their position in the naked index. What we need to do? We need to use component replace items. I will use these vertices, so original position of the vertices, and I'm going to replace only vertices that we move. So these guys I will place in the list, and replacement index for each item we can take from here. Now we can construct the mesh, and faces I will take from here. So this is how we created one part of the mesh. Let's zoom in. Not sure, is it visible? Now we need to create upper part of the mesh, which will be if we take closed vertices, these guys, and I want to move them along normal direction, but we need to take only normal direction of the clothed vertices. Here we have their index value. So here is the index, here we have the normals, and we need to create the amplitude. Amplitude now will be the height, so it will not be divided by 2, and I'm going to place it. All right, now we get the position of the inner vertices moved along normal direction by the full thickness of the mesh. So for construct the mesh, we need to place these points at their exact position. So once again, I'm going to replace items, but now we're not going to replace original mesh. I'm going to replace them with the indices from here, because I want to keep new position of the naked points. These are the items that I want to replace with. And now we need to take their indices. Indices we can take from here. And now we can construct mesh. So these are the vertices. These are the faces. Once we get these two parts of the mesh, I'm going to merge them to place them inside each branch. But you can see here, let's take param viewer. We have 8 branches, but we should have 4 branches. This is why we need to simplify in order to get 2 branches inside each branch, 2 items. Now we can join mesh, single mesh inside each branch. And if we bake this one, let me show you what we'll get. You can see the shading of this. It will get quite smooth shading of the mesh, which I don't like. So to fix that, I will use component mesh explode and turn off the preview, because it will take a lot of time to calculate the preview in the viewport. And if we use something like this, I'm going to join the mesh once again. Let's delete this one. After joining once again, use unify mesh, and I will turn the preview off of the join mesh, and I'm going to bake unify mesh to see the difference now in the viewport. Now you can see that there is no weird shading. All right, let's delete this. And in the last step, I'm going to split the mesh. The mesh will be, actually these 4 meshes will be split by the circle that we have. So I'm going to take this circle, scale it. Center of scaling will be our original point. And let's scale it by 2. And once we get a scaled circle, I will create a surface from it. And now we can use component mesh split. This is the mesh to split, and the mesh will be split with a boundary surface. And inside each bench we have 2 items, and I'm going to extract item with index 1. Let's turn on the site model once again. We get a final result, and we can bake this to see the final shape. In the extended tutorial, we'll create the whole dome design in Grasshopper only. Rather than drawing the model in Rhino first, we'll use Grasshopper components to create model fully parametrical, allowing us to easily adjust it with a few sliders if needed. By following this tutorial, you will gain an understanding of how to speed up your modeling process by incorporating more parametric principles of model variations. You can get access to the extended tutorial on our Patreon page, and with that you will get access to all of our other extended tutorials and project files. The link is in the description. If you'd like to know exactly how to create complex projects like these, and if you're interested in step-by-step learning approach starting from zero, make sure to check our Grasshopper Complete course, where you'll find over 60 hours of video material structured in a form of video library, covering in depth more than 500 Grasshopper components through practical examples. And you'll have access to us personally, so we can answer all of your questions right away. The link is in the description.